Yes, floor is yours.
So, well, thank you for the invitation. Actually, I'm not going to talk so much about uranium telluride, but about the technique that we used to derive the physics that Seamus also measured in his STM experiments. And I just wanted to give more details about the technique that we've been using, which I think it's quite nice and not very well known or used. So this is in this technique, we calculate the edge nodes and the surface Green's functions of a system using an impurity-induced states using the additive matrix formalism. So I'm going to give you the detail. So, but first of all, please interrupt because it's not. I don't want to be like just I'm talking and you are just listening. It's very good if we have some interaction. So please feel free to ask questions, interrupt me at any time because it would be nice to like this. The message is passing much more easily. Okay, so this work has been done with my student Emile, Adeline from Marseille, Catherine, and also the experimental group of Seamus Davis. Of course, they performed measurements and we had a lot of discussion about the uranium telluride subject. Like that. Okay, so now the technique. So we aim to calculate boundary modes using D-matrix. You probably are familiar with the subject, or maybe a bit. You have an infinite system. We all know we can calculate Green's function. We can study the physics. It's a spatially invariant system. We know everything about it. We write a Hamiltonian. We write Green's function. We calculate things. We use diagrams sometimes. But if we have a semi-infinite system, things are much harder because the system is not spatially translationally invariant. So then the physics is a bit harder. Some people use numerical methods to calculate the boundary modes. Some people have, some recursive Green's function techniques and all sorts of other techniques. But in general, it's non-trivial to study the boundary of a given system. So what we do, we start from an infinite system, be it 1D, 2D, or 3D, and then we add an impurity in the system. Then probably now, if you have a single localized impurity, you can always use T-matrix and calculate exactly the Green's function of a system. If the impurity is fully localized, like a delta function, then the problem is exactly solvable, and you can know everything about the system. You know the Green's function of the system, and from there people obtain like pseudo oscillations. They obtain bound states, Majorana states, things like that. Actually, no Majorana states, just bound states, impurity bound states. So what we have been doing is we take this impurity and then we make it to be infinite. So when this impurity is infinite, then your system is automatically broken into two pieces, semi-infinite pieces. So then now when you have the exact physics which the T-matrix formalism is giving you, you automatically have the physics of the semi-infinite system. So either a semi-infinite wire, a semi-infinite plane, or like a slab of 3D material. And it's all, again, very, very simple. We start with impurity, use the T-matrix formalism, and then you have your Green's function. So this is a very nice scheme for somebody who doesn't do a lot of numerics. This is very nice because you have just a simple analytic formula for the T-matrix, and then you do some numerical integrals over one dimension, which is very trivial. I mean, anybody can do it. It's not really numerics. It's just the integral, and then you have all the physics you want. The mathematical concept is not completely new. I mean, I think people looked at boundaries using impurities, but it was very obscurely mentioned in some very old paper, in some appendix, and also it was recovered a bit by the group of Alfredo Leviati some years ago, but again, this paper was not really centered on this. It was mentioned somewhere on the side. Actually, I had no idea about Alfredo's paper when we wrote our things, and then I saw that he was citing us, and then we cited him, but they haven't developed this. I mean, they just mentioned it somewhere in some, on the side in one papers, and they didn't follow it further. For us, we just really focused on it and use it in a lot of systems. I mean, and I'm going to give you examples now of this, how we use this technique for various systems and how well it works. So then we really started like a full direction of research on this. Okay, so next. Okay, so now a few technical details. I don't know how, probably you are well familiar with diagrammatics, and I'm just going to give you the T-matrix formalism, schematics. How does it work? In a few formulas. I'm not going to be very technical, but I'm going to just give you the basics of the T-matrix. So we start with the Hamiltonian in momentum space. Then we calculate the Green's function, which is the inverse of the Hamiltonian roughly. Then we add our perturbation, which is the impurity. And again, this impurity is localized in space. So that's when we take its Fourier transform, the Fourier transform is independent momentum because the delta function potential in space translates by Fourier transform into scattering independent momentum in momentum space. So then we want to calculate the Green's function of the perturbed system. But now the perturbed system is no longer spatially invariant. So we cannot define a Green's function which depends on a single value of the momentum. What we calculate is something which is called the generalized Green's function, which depends on two momenta. So this captures the fact that your system is no longer spatially invariant. So the fact that you have two momenta here, it allows you to capture this non-spatially invariant physics. And how is this quantity being calculated? We start perturbatively. We start first by putting the first order perturbation theory in the momentum scattering, and then the second, and so on. And then we see that the sum of diagrams can be performed exactly if the V is independent of momentum. So the sum of all these diagrams to all orders is what we call the T matrix. And it has this formula. I'm not going to tell you how it's being calculated, but it has this formula, this T matrix. And then we know exactly the formula of the generalized Green functions as the function of these two momenta from the starting Green's function of the free system, of the pristine system. And here I'm going to come back to that often. We have our generalized Green's function which depend on multiple momenta. And here, for example, in 2D, I have two momenta in the perpendicular direction, because in this direction I'm breaking spatial translational symmetry. So this Green's function depends on two momenta on the perpendicular direction and on one momentum parallel, because along this direction I'm not breaking the spatial translation invariance. So then my Green's function depends on three momenta, two perpendicular and one parallel. And it has this formula which incorporates again the T matrix. And it is exact. So this formula is exact. So now my system is described by this exact Green's function. Okay.
Sorry, can I ask a question?
Sure.
How do you go back to real space then?
That's a bit more tricky. Yes, depends on what you want. I mean, you always have to, how do I say? Depends on the quantities that you want to calculate. So if you
create some Green's function, and I want to use the same Green's function as a function of t and x at a specific point in the system. So what do I do with k1 and k2? You're
not going to have a Green's function of x, but you're going to have a Green's function of x1 and x2. Same as for the no longer the Green's function in real space is not going to depend on x1 minus x2, right? Because that's what, but it's going to depend on x1 and x2, and then you just perform a Fourier transform of these Green's functions along the two, with respect to the two x's. And then you have a generalized Green's function for the two with two values of x. And from there, we can calculate whatever quantity you need. For example, the density of states as a function of position is imaginary part of g of x and x. You evaluate at the same position. So that you, for example, the real space density of states. And you're going to see that you're going to go a bit in real space, and you're going to set we're going to keep k in one direction and x in the other direction. So like that, we are going to focus on the spatial position parallel to the wire, and we're going to get the Green's function as function of this momentum. So we do a sort of also mixed Green's function between momentum and space. So, okay. So now again, what I said before, I'm taking by impurity to infinity, and then this Green's function is the Green's function of the infinite system cut in two. Before, the formalism on the previous page was valid for all v's, but now if I'm taking my v to infinity, then this Green's function is the Green's function of the semi-infinite system. Again, I said that before, a boundary is translation invariant, so I have one momentum in this direction and two momenta along this direction, because this direction is non-spatially invariant. So from here, I can get information about the boundary, about the translation invariant boundary, and this can be an edge or a surface or a point, or about the perpendicular direction. But along the perpendicular direction, the only thing that I can calculate really is the density of state as a function of position. I mean, I don't have any more momentum dependence because there is no more good quantum number, the momentum. And this formula is valid for all dimensions, 1, 2, 3. But in each direction, in each dimension, we have other quantities that we can calculate. So it depends on the dimension what we are looking at. Okay, so now I'm going to give examples how this works to see that it's actually working nicely. So I'm starting with 1D. You probably are familiar with the subject of Majorana states in 1D. So we know that we have topological wires, what we call them. We have some models, and these models have some bound states on the edges, which are supposed, in the models, they are Majorana states. And experimentally, there are debates if we really can have these states rising. The simplest models that can have these bound states at zero energy on the end of the wire is what we call the Kitaev model. And it's a very simple model. We have a chemical potential, you have some hopping, and you have some pairing. This pairing is coupling two sides, the two nearest neighbor sides. And it's quite nice because from such a simple model, when you solve it, for example, numerically, you just plug your big matrix, your Hamiltonian matrix for this wire. You have each side is one line element of the matrix, and then you make a big matrix. You have 100 sides wire, you make 100 by 100 matrix, and you diagonalize it. You get its eigen values and eigenvectors. And when you do that, you see that you have some bound states which are localized on the ends of your wire, and they are at zero energy. And if you look at their specific wave function, you see that they have an equal superposition of electrons and holes, and they are what we call Majorana states. So this is what we know numerically, for example, about this model, that it has these states which are Majorana states.
Sorry, in this case, what's the gap energy? Is that 1 in terms of your energy?
I think the gap is around 0.1. There's a gap. I think the delta that I choose here is 0.1. Yeah, there's a gap. This is the gap.
Okay, so the density of states is not an in-gap state, but it's...
No, the states are in-gap, so this is the gap.
Right, but so the purple stuff in between, so on all the sides except 0 and 100?
No, this is the gap. This is the gap edge.
Okay.
This is the gap edge, and here you have the states which are above the gap, and inside the gap you only have these two Majorana states. So my gap edge is just purple. That's my gap edge. So then I do now, using my technique, the same. I'm solving the same model using my technique. So I'm getting my infinite wire. Here I can actually do 2 impurities. I can do only one, but okay, in the paper already 2, but we can do 1 or 2. We can do both. So we see that when I'm solving my model, I have my Green's function, which now again non-spatially invariant. So it depends on K1 and K2 along the wire. And when I integrate over K1 and K2, and I'm going to real space, like you asked here, and I'm taking the Fourier transform of this Green's function with respect to momentum, but I'm keeping I'm keeping here the two spatial position identical to get the density of states. So I have my G of x1 and x2, but to get the density of states, I keep x1 equal to x2 to get my density of states. So my density of states would be given by this formula. And I plot it as a function of energy, and position. And then you see that I recover very nicely exactly the same Majorana states that have been obtained numerically. So I have my gap edge. There are different parameters that I chose between these two techniques. Here I think the gap is 0.3, here is 0.1. They are from 2 different papers, so I just put them side by side. So I have my gap. I have the states above the gap, and here I have the density of states at 0 energy on the 2 ends of the wire, and these are my Majorana states. So using my technique, I recover exactly the Majorana states that have been calculated numerically before. Okay, so now the procedure goes on for various systems in various dimensions. So for example, in 2D, I'm going to get exactly the same, I'm going to apply exactly the same type of procedure, with a big, small difference, whatever, that now I have another direction that is spatially, that is translation invariant. So now I have a free momentum, like a free quantum number that is py along this direction, the direction of my ribbon. Along this direction, I have finite size. So my states, my eigenstates are quantized. So I don't have a continuum because I have a finite size system. So I have quantization of the modes. So when I solve numerically this system, I'm getting this the regular states of my system, plus inside the gap I have this propagating edge mode. So this edge mode depends on the momentum parallel to the wire. And this is what we call like chiral Majorana states because they form on the edges of my ribbon, they propagate, and they have the wave function, which is characteristic of a Majorana state, equal combination of electrons and holes, and they cross zero energy, of course. And the model that we've been using is just the 2D generalization of the 1D model above. It's just a 2D type model, so it has the same physics. But now my hopping is like in both x and y direction, only in the x direction. Okay, so this is numerics. Okay, so now we use our procedure again, no longer numerically, but analytically. And I want to stress again, it's very easy to use. I mean, you write your Green's function, which is the inverse of your Hamiltonian, or whatever, and then you apply the T matrix, and in one formula, you recover this Green's function, which depends on 2kx and 1ky. And then we do a trick to get the actual physics of the edge modes. We do the Fourier transform of this Green's function with respect to one direction. So we take a double Fourier transform, but with respect to the x direction. So we integrate over k1x, k2x with the corresponding phase factors, and we focus on x equal x prime equal a. So we are just at one lattice spacing away from the input. So when we perform the Green's function, when we perform the Fourier transform of my generalized Green's function to get the edge mode, I just sit at one lattice distance away from the impurity. So this is giving me the physics at this x, but as a function of ky. So now I have a physics. My physics now it's localized in space, and it depends on the momentum parallel to the impurity. I mean, does it make sense? So it's like I have a 1D physics now. I no longer have a 2D physics at all. For the edge state, I have a 1D physics. I'm just basically recover some effective 1D Green's function for my edge line, because I localize my physics at this position, and then it's free. The ky is free in this direction. So it's basically writing the Green's function, effective Green's function for my edge state. And this is very nice because then I can calculate by taking just the imaginary part of this Green's function, I have the spectral function. So I've been plotting here the spectral function for this system. Here I'm actually not even plotting the spectral function at the edge, but I'm doing some sort of average spectral function over all the system. So that I can count the bulk modes and the edge mode. So here I have both the bulk and the edge mode. And you see that indeed I have my bulk modes here above the gap, and I have my edge mode here inside the gap, which is chiral and propagating. So, okay, this is, I mean, I think it's very nice because with one line of calculation, yes.
Your color scheme, does it mean that the propagating mode is at 0 or?
They're crossing 0. No, it's not at 0. It's actually, yeah, the color scheme is not very well chosen, the color scheme, but this blue, I think, is this blue is 0. I think this was positive and the red was negative or the other way around, but this is a delta function. It's not sorry, not delta function. It's a variation from some background. So then some things appear with plus, some things appear with minus. The color scheme is very bad in this figure. Sorry, I mean it's not really. So ignore the color scheme. It's just that you have this mode here and this mode here. We changed the color schemes and the way we represent our mods in the later papers, but this one was the very first one, kind of. It wasn't very, very nice. Okay. Okay, so what was I saying? Yes, that now by just performing this very simple integral here, basically this is just the inverse of the Hamiltonian. This is your integral that you have to perform, and that's all. And then you have your I skipped one step. To get this, you need another integral. So you have a few momentum integrals that you have to perform, and that's it. I mean, all your formulas with a few momentum integrals, and you have all your physics for the system. Okay, so now to the subject of the physical subject of this talk, uranium telluride, which uranium telluride is a 3D system. So I'm going to do the same procedure, but in 3D. and to study the physics of uranium telluride. So now uranium telluride is a 3D material, and it has two per unit cell. It has 2 uranium and 2 tellurium per unit cell. So from here, from these 4 atoms, I'm going to get 4 bands. And the Hamiltonian, the tight-binding Hamiltonian for this system has terms which describe nearest neighbor hopping between uranium atoms, between tellurium atoms, and some hybridization between the uranium and the tellurium bands. We're not going to put this by actual tight binding, we are just putting phenomenologically at the end, the hybridization between the uranium and the tellurium bands. So the one model, the recent model which is describing this, and I have to say it's a mess. I mean, there are a lot of, the terms that you can put. I mean, it's a very messy model. There have been some older models trying to describe it, either with only with 1 band, 2 bands, and it was very accurate. So this is very recent. I mean, like just 2 years ago, there was a more complete model, including all the bands, a 4-band model. But still, it's quite messy. So then it has a lot of parameters, of course. So then you can get a lot of combinations of parameters describing your model. So there have been like, for example, sets of parameters described that have been used to describe the physics of quantum oscillations. So the size of the Fermi surfaces. There have been like some parameters derived from DFT, and they are not the same. So that's quite funny. They are not exactly the same. So you can get a lot of variability. So, and even us, I mean, we used some adjusted parameters to fit the Fermi surfaces. And there have been other papers which use other parameters. So that, the space of parameters is kind of not very well fixed. So I think, yes.
Is there ARPAs on this system, or is it too messy in terms of cleavage to do any measurements?
No, I don't think so. There is any ARPAs. At least I'm not familiar with any ARPAs. And I think it's quite messy. You can cleave, experimentally cleave on the 0.1. And I'm not aware. Maybe there are, but I'm not aware of ARPAs. It would be nice with ARPAs, but I don't know. I'm not aware. Maybe recently, I don't know. So again, there was even another paper that did similar stuff with ours, and they are using very different sets of parameters. So you may just even sit in a different band. I mean, the bands are kind of similar, but sometimes you put your chemical potential in one band, sometimes in another band. So you have to be really careful. I mean, this is a really tricky system to keep track of. Okay. So just a few words about the model, though I'm not going to tell you too much about it. I mean, you have, again, the uranium and the tellurium Hamiltonians, the tight binding ones, and the hybridization term, which is phenomenological. You have some terms which describe hopping, on-site hopping, and intraorbital and interorbital hopping. I mean, you have this type of terms. So you have, again, a big tight binding model with a lot of parameters that you can play with, like I said. So you have 4 orbitals, you have 2 spin, and then if you want to look in superconductivity, you have also electron hole. So your Hamiltonian is 16 by 16 if you want to do superconductivity, if you want to look at superconductivity. It's quite a big matrix. You have a 16 by 16 matrix to play with, which is not always trivial. So now superconductivity, you don't have to ask me too many questions about it because I'm not very, a specialist in this. The idea is that you can use different type of order parameters, different type of couplings. I mean, you can. There is not a single way to introduce superconductivity in this system. People usually use a nearest neighbor interorbital pairing. With delta 0 pairing strength, but I think there are versions of that. Some people also use intraorbital or whatever. So it's not, this is not also not very well established what type of superconductivity terms you can have. And the most importantly, you have different type of order parameters with different forms in momentum space. So you can couple you're introducing your superconductivity in different ways. So you have chiral, you have non-chiral order parameters. So you can have this type of delta, this type of superconducting vector. You have A, U, B1, U, B2, U, and B3, U. I don't know why they're called like that, to be honest. I mean, I just know that they have different type of pairing, pairing form in momentum space. What I know that they give very different physics. and that your surface states are actually the physics is non-chiral. It's not like in the Majorana. It's not propagating like in what I showed before for the Majorana. But you can also obtain chiral order parameters by combining these two. I mean, you can use 1 plus I times the second one for the pairing. So then you obtain like chiral order parameters. So you have a lot of possible order parameters for the system. You have these 4 non-chirals and then all combinations you can make, which gives you a lot of order parameters. So now how do you actually choose between these order parameters for your actual physical system? There must be a way to figure it out, which one is the relevant one. So that's what we did with Seamus. They performed STM measurements, and then QPI, they studied the QPI features, and we tried to make the connection between our calculation and his measurements to see which of these order parameters is the most likely one describing the data. And in the paper that Seamus wrote previously in 2025, their measurements, also STM but not QPI, they showed that actually their data, their preliminary data on this STM data that they showed in 2025, they're actually consistent with non-chiral order parameters. So we reduced our analysis to the non-chiral ones to compare with the STM data. Though, I mean, we also did a calculation for the chiral ones. I mean, there was, since we had the mechanism, we did it for every order parameters, but okay, the results that I'm going to present and the ones that we sent on in the paper are the non-chiral ones, because that's what he claimed to have seen in the previous paper. Okay, so now I'm going to make a parenthesis from uranium telluride, and I'm going to go back to my technique. And I'm going to repeat once more how I use it for the 3D now, for the 3-dimensional system. Again, the same procedure. I take my infinite system, I cut my system, but now my impurity is no longer a line or a point, it's a plane. So my impurity now is a plane. So it's uniform in 2 directions, and it's, it's breaking symmetry in 1 direction. So now I have 2 momenta, like in kx and ky, which are a good quantum number. I have translation invariance in 2 directions, so I have a surface. So my potential is delta function in this perpendicular direction, and I'm going to use a matrix which again is 16 by 16 because that's going to be my Hamiltonian later. I'm writing my T matrix for this system, which always depends on this good quantum numbers in the plane parallel to the impurity. I have my generalized perturbed Green's function, now depending on K1 perp, K2 perp, and the K parallel. And it's written in the T matrix language. So it's exactly the same procedure, now that my free parameter is in a plane, is not a line. And I do exactly the same thing as I did before. I take a Fourier transform in the direction perpendicular to the impurity to actually get some effective physics on the plane parallel to my impurity at one distance, one lattice distance away from the impurity. So here I'm projecting on the 0 and 1 plane. I mean, that's experimentally, that's the only plane that they can do measurements on. I think there's a cliff plane. Yeah. Anyway, so that's the plane on which they can measure the 0, 1, 1. So I'm going to choose a direction parallel to that surface, and that's why I have this lattice spacing, which is a bit bizarre. I mean, in terms of the lattice distances A, B, and C, I have this formula for the 0, 1, 1 distance from the impurity plane. So I have the Green's function effective Green's function on my surface. And so I want to study my surface. I have the effective Green's function, and the first thing I'm going to plot, even if it's not measured experimentally, is the surface spectral function, which one could measure, for example, in RPES for a 2D system. So I'm first plotting that, the surface spectral function, and then I'm looking at the QPI as the next step. Before the QPI, I'm also showing you how to calculate the density of states as a function of energy, which is also measurable in STM, either in the bulk or on the surface. You can either integrate the Green's function of the bulk, or you can integrate the Green's function of the surface to obtain the density of states as a function of energy. So experimentally, this cannot be done, at least I'm not aware of the spectral function, but this is measurable, like especially the surface density of states has been measured by Seamus. So I'm going to show you the comparison. And then we go to, but for now, do the first steps. So please ask questions if it's not clear. It's not very, very complicated technically, but still it's not, straightforward. So if there's something not clear, please interrupt. Okay, so then I repeat for the 100th time. I have my effective physics on the plane. I have the Green's function, so I have the spectral function from the Green's function, and I plot it as a function of the kx and ky. So I'm on the surface. I have two momenta and one energy on the surface. It's like any 2D system that you study, like graphene or anything. You have two momenta and one energy, and you have a spectral function. So you can either fix your energy and plot the spectral function of the two momentum, or you can fix one momentum and then plot along a different direction of the momentum as a function of energy. So you can either do this 2D plot, or you can just go along one line and one cut and then plot as a function of energy and momentum along this direction, for example. So you see the spectral function for the normal state. It's just one energy, because for the normal state, we don't have a gap. So if we don't have a gap, for energies which are very small, my band doesn't depend on energy. So then I don't care at what energy I'm plotting, because my physics is basically independent of energy. So I'm taking one energy, and then I'm plotting the spectral function. It's a bit bizarre. I mean, you're going to ask me, why are these blobs? I mean, honestly, I don't know. I mean, you get some blobs, and these blobs come from the projection of your Fermi surfaces on the 011 clip plane. Why they look like that? Well, you really have to look into the details of the Fermi surface. They just look like that. I mean, they have some high intensity regions here. Okay, I mean, that's your basis. At along the 011 direction, you have this type of spectrum. If I were to calculate along the other direction, which are more symmetric, like 001 or 010, then you'll have something a bit more readable. But since I'm looking at this kind of bizarre cliff plane, then I have something a bit more funny. What is important is this is my basis. I mean, this is a normal state. This is my basis. And then I add superconductivity. So I'm going to focus on only on two of these order parameters out of the four ones that I told you about, the non-current ones. I'm going to focus on B2U and B3U, because those are the most likely to correspond to the data. And I'm looking at zero energy, and B2U has the spectral function, which looks very much like the normal state. So it doesn't have a lot of intrinsic physics. You don't have a lot of intensity. So you'd expect to have some sort of a gap in the spectrum, and it is indeed what's happening. You don't have any surface states which cross zero. So you don't have any of this Majorana type, like topological nice states. You have some states on the surface, but they are gapped. So for sure, they're not topological. They're gapped, and they don't cross zero. So I don't know, probably you may have run into this problem before. Not all surface states are topological. And not all surface states are gapped. Sometimes you form surface states which are not topological and gapped. So this happens in nature. I mean, you get a lot of these states, not all of them are. So they are only appearing on the surface. They are not there in the box. They are new physics, which only appears on the surface, but they are not topological nor crossing zero. So this is what happens for the B2U. You see that you have a gap. So your surface states actually I don't know if they propagate. Anyway, they have a dispersion, but this dispersion doesn't touch zero. So there are some sort of gapped surface states. And if you plot now the density of states on the surface, you see that you have a dip, you have a gap. And
Yes, but so you still have some intensity in the zero energy plot, and you still have quite a lot of states at zero. So
yeah, because
you have unpaired electrons, or
no, but I have a lot of finite width. I have levels with very big finite width. I have a lot of, you see, this should be like very thin lines, but they are not. So because we are using the line width to correspond to the experiment. So you get a very big dissipation. I mean, you have a big, in your Green's function, you always put some artificial broadening of your levels. Okay, I have a big broadening of my levels because to make connections to experiments. In the experiments, the broadening of the level is very big. So then I'm using it. I should have, I think we have some data, but I didn't put them in the presentation. I should have put it somewhere. I don't even know if they're in the paper, in which you choose broadening, artificial broadening, which are much smaller. So then you see much better these states. I mean, they really are like that. I mean, they don't touch zero. There is not no intensity on the. You only have some intensity which comes from the projection of your bulk. Sometimes the bulk just projects on the surface, but then the extra states don't have any intensity. Okay, so B2U is not very interesting, but B3U is nice because you have a lot of intensity at zero. I mean, you have states which are really zero energy surface states. And when you plot the dispersion with respect to energy, you see that they actually do have a peak at zero energy. So they are more or less localized around zero, and they tend to propagate a bit around zero. But I have to be honest, they are not exactly zero. I mean, they are a bit gapped. It doesn't show here, but if you really do more, smaller, finer broadening, and if you really look in detail, you see that they are actually a bit off zero. So these are actually not exactly symmetric zero energy nice states like you'd expect for some nice topological states. So okay, they look good. They have a lot of intensity at zero. They can fit the experiments because in the experiments in the dots you have a peak at zero, but it doesn't tell you that these are topological states. They just tell you that you have zero energy intensity, a lot of zero energy intensity, so a lot of zero energy surface states. And now we are actually trying to understand if these states are topological and what states are actually topological in this system. And this is a non-trivial question, actually. And I think the 011 surface, since it's very asymmetric, doesn't really have topological states, cannot actually have topological states. So in the literature, there's a lot of confusion because many people say, oh, topological states in uranium telluride and this, but well, they're not, nobody actually checked they are topological or not. So I think on 011, you cannot even have some topological state because of symmetry. So you have to pay attention when you're writing things about this system, if you call them topological or not. So that's confusion in the literature about it. So now that's the spectral function and the density of states as a function of energy. And now to the QPR. But what is nice about this system, what's really even more interesting about the measurement of Seamus is that you can measure the density of states as a function of position in the presence of impurity on the surface. So now I have to forget everything I told you till now about the T matrix, because imagine that basically the bulk doesn't exist anymore. I just have a two-dimensional system which has a Green's function, an effective Green's function. So it's the same as having a sheet of graphene. I have my two-dimensional system. I know its effective Green's function, and I measure it. I put an impurity. Now I put a localized impurity, and I measure the Friedel oscillations generated by this impurity. So this is what Seamus is doing in his experiments. So forget about the bulk. We have the surface. We add an impurity, and I have some nice, Friedel oscillations close to in the vicinity of this impurity. And not unfortunately, but the name of the procedure that allows me to calculate the physics in this plane is also a T matrix. So it's the same. It's also a T matrix, but now it's not a T matrix in the bulk. It's a T matrix around the impurity in 2D. I have again one localized impurity in 2D, and then I can calculate the density of states around the impurity using T matrix again, but now a different type of T matrix. It's a 2D T matrix now with a localized impurity, 1 point impurity in 2D. Before I had a line impurity in 2D, or a plane impurity in 3D, or a point impurity in 1D. Now here I have a 2-dimensional system with 1 point impurity. Okay? So now I'm calculating the density of states around this impurity. So this impurity is not something to cut my system into whatever many portions I want, but it is an impurity to really generate oscillations on the surface plane that are measurable by STM. But the same mathematic applies. I have a Green's function, effective Green's function for my plane. I calculate the T matrix, which has the same type of formula, and I calculate the effective Green's function of my 2D plane in the presence of the impurity. But what I'm going to do now from this quantity, it's going to be a different type of, processing. I'm going to, you see, I have two momenta here. I have K and Q, and I'm going to integrate over one of them to actually recover the density of states as a function of momentum, which is the Fourier transform of what is measured in real space. So what the experiment is doing, you take each position, you measure the density of states, you go through all the spatial points, and then you calculate the Fourier transform. And your Fourier transform is going to be dependent on momentum because it's Fourier transform. And the nice thing about the analytical calculations is that the same Fourier transform can be obtained using this formula from the generalized Green's function. I'm not going to show you that. I mean, if you can go through the definitions of the Green's functions and the whole Fourier transform, so you can play with all these formulas, and you're going to see that it's the same thing. I mean, the Fourier transform of the local density of state is the same as the integral over k of this g of k and q. I mean, you see that if you do the math, you're going to get it. But it's a page of formulas, Fourier transform, and everything. I'm not going to go to that. You have to trust me that this is the connection between the two. So now I can calculate this, and Seamus is measuring. So we just need to compare. I mean, I get my results from my calculation. He's getting his from the experiments, and we compare. Now the comparison. Okay, so now another step back to the spectral function, because in order to understand the Fourier transform of the local density of state, you have to understand where is it coming from. So now I have electrons living into my electrons live in these regions. And these regions are defined by the spectral function. So the spectral function is basically the locus of where my electrons live. So my electrons live here. If I add an impurity, these electrons are going to scatter. So, you can scatter between this and this, you can scatter between this and that. I mean, you have a lot of scattering processes between these places where the electrons live. And in the QPI, in the local density of states, you're actually going to see what you're going to see at the momenta at which these electrons can scatter. Okay, so I'm adding an impurity, I get scattering processes, and the Fourier transform of the local density of state is actually giving me the processes allowed, all the scattering processes between the electrons. So basically, it's some sort of an inverse RPS. I cannot have the spectral function measured, but I have the QPI, and from the QPI, I can go back a bit and see where my electrons are living. So, okay, if I have a QPI like that, it's consistent to having my electrons living on surfaces like that. But I cannot actually go. Maybe now the AI can do that and give it like some, some sort of QPI, and then maybe it can recover the locus of my electrons. But well, it's usually did by hand. Try to do it by hand. Maybe now the AI can do it. So the order 0 of predicting the QPI, he's saying, okay, I have this electron scattering here, this electron scattering here, and I'm collecting all the possible scattering processes into this type of map. And this is what is called the autocorrelation of the spectral function. I multiply it with itself, and then I see where does it superpose, where are the regions that superpose are the strongest. Okay, so then I do this type of autocorrelation, and if I plot it, I'm going to get something like that. I mean, it has a lot of high intensity regions, which are going to describe, the superposition of the spectral function with itself. Okay, so this is you see that here I have a lot of possible a lot of possible intensity in a lot of places. But if I do it exactly, I mean, this is just intuitively. I take the spectral function, I autocorrelate it with itself. But then it's not exact because some processes are forbidden. Sometimes I cannot scatter between this and that, or between this and that. I have some opposite spin or other type of forbidden terms. So when I actually do the exact calculation, I get something else than the autocorrelation. It looks a bit similar, but not really. So for example, here, I mean, I have a lot of intensity here, and I don't have it here. So for the normal state, I see that I mostly have this type of scattering processes, this type of intensity here and here, which corresponds to scattering between this region and these regions, and between this region and this region. So the normal state QPI is going to be dominated by these two vectors. And again, just autocorrelation is going to give you a lot of other stuff which is actually not there, it's not physical. So you have to do the exact calculation with the T matrix and everything. You cannot do just autocorrelation of the spectral function. In a lot of fields, people just have the spectral function and autocorrelate to predict the QPI. But sometimes it works, sometimes it doesn't. It depends on what type of, if your Hamiltonian is very complicated, if you have a lot of, scattering of matrix terms, which, give cancellations. In graphene, there's been a lot of there's been a lot of discussion about it. Like 15 years ago, you had some regions were forbidden by, they're forbidden to scatter, and then you're having empty regions instead of circles as predicted by the autocorrelation. So there's been some discussion about that, explained using the chirality of electrons in graphene and everything. I don't know if you follow that. Okay, so now here you can see though that this region is missing. You have Q2 and Q6 for the normal state. But you see now that even if you start from the same type of spectral function, B2U and B3U are going to give you different QPIs. So B2U is going to have a very small intensity, but you can still calculate the QPI even if the intensity is not going to be too large. And you see that you have Q2 and Q6, like the same wave vectors as in the normal state, but you get some extra intensity here. You have a Q4 and Q5, which correspond to different types of couplings. This is Q4 and this is Q5. So you have this a different QPI for B2U. And for B3U, which interests us the most, you have an extra wave vector here, which we call Q1, which corresponds to scattering between these two regions. So I have the same Q2, Q6, Q3, Q4, Q5, but also this Q1, which is this big blob here, which was not there, neither here nor here. This extra blob, Q1, which corresponds to scattering between this and that. So that's why the B3U physics is different, because of this extra peak, which is allowed by the symmetry of the order parameter, more or less. Okay, so now we can compare our predictions to experiments, because again, when you measure the density of states and you take its Fourier transform, you get this what we call QPI, quasi-particle interference patterns. And this is 2D plots obtained by Sims at various energies. And these are calculations for B2U and B3U. I'm only putting these two. And you see that they don't look too bad. You have some intensity close to zero, zero momentum here in the center. That looks more or less similar both for B2U and B3U. And it would look, this would correspond to the Q3, 4, I don't remember exactly the number. It corresponds to Q4 and Q5 terms, more or less, wave vectors. And then you have this Q2 and Q6 here. Sorry, Q2 and Q6, here in this two, I think. No, well, anyway, I forget the names, but you have this one that are universal in the normal, in the B2U and the B3U. And then you have this blob, which is actually looking very much like what Seamus is measuring also. So this would be the extra peak, which corresponds to our Q1 peak in the B3U. We checked, the wave vectors, if you check there exactly, this would be like Q3, Q4, Q2, Q6, they fall on the same. So this is the same correspondence in here and here. This is an exact correspondence. So these peaks are fitting exactly. And this is a Q1. This is a Q1, the correspondence between the experiment and the theory. So I think we said that it's working pretty well. We have this extra peak, which is there in our B3U, is not there in our B2U, and is there in the experiments. So we made the correspondence, and then because of that, we said that, okay, B3U is the most likely one to fit the experimental data. And
can I ask a question? Sure. So what you get out depends very much on what you put in the sense of the Fermi surface. And you already said that there's quite some differences in what to use, maybe also what spin texture to use. So to what extent will this affect whatever comes out?
Yeah, it's stable in the sense that there is always this type of peak. But what is not stable is how dispersive it is, how exactly far from the center it is. So you have to play a bit of parameters to make it look exactly like the experiment. It's there, but it's hard to find it, to fit this exact position, exact dispersion. By playing with Fermi surfaces, you get a lot of variability. Yes.
Right, but you can never get it for the B2U. Is that correct?
Yes, exactly. Yes. Yeah, exactly. Mm-hmm. Yes. we want to play with some more set of parameters, some different bands and things like that. We want to look into that, especially because we are interested in topology. So we are trying to look more into the parameters of the model to see how general it is and how much we can. Because there is another group who actually looked into this problem, and I think they're seeing similar stuff, but not exactly like I said. I mean, so we really have to make correspondence with what they saw and, to see if we are going in the same direction. I mean, in general, the general features are the same, but the details are different. Okay, and another feature which works well with the experiment is that you have a peak in the DOS, like I said before, at 0, because I had this 0 energy state. And I don't have it in B2U, I have it in B3U, and experimentally you have a peak also at 0 energy in the decisive states. So that's another argument that the B3U is the one that fits best the experimental data. Okay, so I mean, if you have any other questions about B3U, because that's more or less my my discussion about B3U. I have, sorry, about uranium telluride. I have a few more slides about other things, but uranium telluride, this is more or less it.
Is the width of the peak in theory, that's because you introduced this broadening, but if you look at the experiment, the broadening is much less. So would that mean that you could have used a smaller broadening?
Yes, but then again, it's hard to fit everything with the same parameter. So I mean, even the broadening you have to play with, because you have this peak, which is also telling you something about the broadening. You have the broadening of the peaks. You have to play with it to get it.
So what if you use the broadening of the spectrum and then calculate the QPI? Does it look very different?
But no, there's the broadening of the spectrum that you use to calculate the QPI. We use the same broadening here and here.
Yeah, but so let's say you use a broadening that matches the experiment.
Here you use a small broadening. It will be still the same, only that the peak is going to be like finer, exactly like here. Just that it looks a bit uglier, because not uglier. It's going to look more dispersive. But it's it's going to still be a peak. It only will be like smaller. And what did I say? But I think we are not only using it as a fit parameter, the weight, but actually it's obtained in the experiment. I think it's estimated experimentally. So we are using the experimentally estimated width, which is quite big actually. So it's really hard to make too much sense of it, but it's quite big. It's like maybe even 1/3 of the gap, 1/5 of the gap. It's very big with respect to the gap. It's quite big. But we've been trying to use that, something more consistent with experiment. Okay. So in the last few slides, I'm not going to say too much, just that I'm going to sell more my technique, and I'm going to give you a few more examples, just a few words about a few more examples. I can do systems with two impurities, like I showed for the Majorana, but like that you can do any finite system you want. You can calculate bound states, and we actually played with calculating bound states, bound states, which is a bit tricky, but we played with. Then we studied 3D system with again plane surfaces. We looked at Weyl semi-metals, and we obtained the Fermi arcs and their QPI. It worked for that. We also have information about the spin polarization of our surface states. We haven't really looked into that too much because there are no experiments done on that. But when you plot your spectral function, you see that you have different spin polarization of your spectral function. So this can tell you what happens if you have a magnetic impurity, for example, things like that. So your spectral function is going to be spin polarized. Just your magnetic structure of your gap and everything. I think you have some. No, you don't have. The whole magnetism is coming from the gap, I think.
So would this be the same as doing a measurement in zero field and finite field and take the difference, or positive and negative field and take the difference, something like this? Or
how would you measure it in RPS? This is the number of electrons with the difference of electrons spin up and spin down, for example. I mean, that's the z direction. So this would be like the rho up minus rho down. Okay, so this would be like the decisive states along the projected in the z direction. So it should be like up minus down here, for example. That's the spin polarized. But I don't know. For now, there are not even normal RPS on these. I mean, to have spin polarized RPS, it's a big step. So we didn't get into detail. We just said we can calculate them. We showed them, but we didn't get into detail. And we didn't perform the QPI because it's messy. I mean, you get a lot of data. You don't know what to do with it. We also looked at graphite. I mean, people usually think about graphene, but graphite is actually, a thick thing, and graphene has 2D physics, but graphite is 3D physics, even if the coupling is not big between planes. And then what happens on the surface of graphite is not always the same as graphene. So we looked at the difference between graphene and the surface of graphite, and actually it turns out they are quite different. Okay, and you can imagine other applications. For example, add a lot of these point impurities to generate a boundary by point, to get the physics of some, infinite system with a hole, or the physics of a finite system, by just using these point-like impurities and applying recursively the T matrix on it, taking the impurity value to infinity, and then do it step by step, and then you're going to get the Green's function in real space for a system which has any arbitrary shape. I did this quick exercise, for example, for higher order topological insulators. I did it for like a 2D topological insulator with corners. So you see that you can recover the corner state. And by just generate the boundary by taking impurity by impurity. And after you put in all these impurities, then you're going to generate the corner state in and out your hole. Okay, and I mean, I'm putting this just to tease you. You can put an impurity on the surface of a 3D system, like I described for uranium telluride, but then look at the Shiba physics. And you can see the surface Shiba states, and by doing the same procedure, you have the Green's function of this surface, and then you add the impurity and look at the Shiba states with magnetic impurity, scalar impurity, polarized or non-polarized. So you can do some work in the direction also. It's cool. Actually, we are doing some work in the directions, but I'm not showing it to you because it's not finalized. Okay, so to conclude, I'm just selling the advantages. Again, it's non-numerical, it's fully analytical. It gives you physics of edge and surface Green's functions using just a very tiny integration over some momentum, nothing else numerical. And you have now the boundary Green's function, not only the boundary modes. So that's important because, for example, the QPI, you cannot study them just by the modes. You need the Green's function. So this is going to give you the full matrix Green's function, and then it's going to give you all the phase factors and matrix elements that are needed to calculate QPI. So all the forbidden processes and everything are going to be incorporated in the matrix structure of the Green's function. So it's going to give you precise QPI. It's not going to be just, it's going to be much easier to implement like that, for example, the QPI. You can take any complex system that you want, and it's, I would say, very easy, but you have to be careful. In 3D, not always directly, how to say, it's not always straightforward immediately. You have to be a bit careful. When you have a very ugly 3D system with surfaces, you have to be a bit careful. But besides that, in general, it's very easy to implement for anything you want. We implement this for many things. So then there are a lot of applications. And another nice thing is that you have a physics of a semi-infinite system, fully semi-infinite. There are no side effects. I mean, because sometimes in tight binding in numerical analysis, you have a finite size system, you have discretization, you have some, bound state that appear, spurious bound state that appear because of the finite size. Here you don't have that because your system is semi-infinite. So you get rid of all the spurious side effects and everything. So that really saves a lot of hassle in some numerical analysis where you have problems with side effects and bound states coming from finite size. Okay, so again, all this is exempt from side effects, so I think it's a very nice technique that can be used in many cases. Okay, so I hope I convinced you. So thank you very much for your attention.
Are there any questions?
Can you fit correlations into the picture?
Sorry?
Can you fit correlations into the picture? I guess uranium.
In the interactions, you mean?
Yeah.
At this point, no. I mean, except if you do like Hartree-Fock type of things that you put in.
Oh yeah, I meant.
Yes. No, I didn't try that. I don't see how. I mean, it's just a effective Green's function technique and T matrix. So I usually interaction don't work with that.
So if you can do arbitrary impurities, you can effectively remake a measurement for example, on the Jameson state where you put all the impurities in the right place? Is this something that's possible?
Yes, you can do. You can do.
Would that be any helpful over the things that you're already
No,
done?
not for QPI. For QPI is not really worth it. It would be in other circumstances, yes, but the QPI not, because then you have to take a Fourier transfer by hand, so it's not really helpful. Because what you get is the Green's function in real space. So then, you know, if you want to go to QPI, you have to do it. So it's not always very useful. Not in this case, it's not very useful.
So, when I understand right, is there an intuitive way to understand the difference between the B2U and B3U, so the presence or absence of this peak in terms of the pairing function?
Okay, if you were to ask Emil, I think you'd find you out, but I don't. So I think my students would be able to tell you, okay, this region has, I don't know what phase, what symmetry, it will scatter into this or not, but I'm not that familiar with all the details and symmetries of the system. So I think Emil, I think will be able to tell you. So.
Okay, no further questions. Thanks, Cristina, again.